Hello everyone, I'm Yujie He from Tongji University, Shanghai, China. In this video, I will present our work towards robust visual tracking for unmanned aerial vehicle with Tri-Attentional correlation filters. First of all, for the people who are not familiar with visual object tracking for UAV, I just explain very quickly what the aim is. Similar to genetic visual object tracking, the goal of UAV visual object tracking is to predict the object's position and size in the image sequence given the initial state of the object from area perspective. On the one hand, existing area platforms have relatively limited computational capabilities. Under the hard constraints of a real-time vision-based UAV system, an ideal tracker should be efficient to gain more computing resources for other important tasks. On the other hand, the object tracking applied to drones face more complex challenges due to the object's appearance variation, such as occlusion, background clutter, and similar objects. Recently, the correlation filter-based tracking method has been extensively studied due to the computational efficiency. The main workflow is that, firstly, learning optimized CF in the frame K. Secondly, applying CF to generate correlation response for classification in the next frame. Then, repeat these two procedures. However, most CF-based trackers use the information of the track object in the current frame. In the process, the circulant shifting operation and extended search region introduce unwarranted noise. Thus, the learned filters are easily corrupted and can lead to unwarranted drift. Some works have been attempted to tackle background clutter or similar objects by applying context learning. However, these methods are not able to employ limited computational resources to the parts that may influence the track object. Besides, the CF-based tracker mostly ignore the potential information about the multi-dimensional response itself or from consecutive frames. Inspired by human perception system, the effectiveness of attention mechanisms become increasingly affirmed by many fields, especially in computer vision for robotics. In this work, we focus on incorporating attention mechanism into CF-based framework. A novel tracking framework with Tri-Attentional correlation filter that is contextual, dimensional, and spatial-temporal attention is proposed to utilize multi-level information to achieve more adaptive filter learning and response generation. So, how to efficiently and effectively apply the attention mechanism? The blue part is the objective function of the baseline method, KCC. The positive and negative samples are regressed to a Gaussian function using the correlation correlators. So when applying the filter to detect the object, you just need to calculate the correlation output of the current image feature with the filter, and then finding the peak position of the generated response. The second term is the L2 regularization, which is widely used in machine learning. Compared to KCC, attentional contextual information, as shown in the red part, is introduced as the negative samples to enhance the training of the correlation filters. Well, S is the number of the patches extracted from the up, down, left, and right to the object. They are considered as the hard negative samples, so the desired output is 0. Besides, an adaptive penalty factor PNS is proposed to evaluate the importance of the content patches and varies along the tracking procedure. The adaptive penalty factor PNS is evaluated as follows. By representing the patch with different handcrafted features, the generated responses corresponding to each context is evaluated with a novel response quality index, PME. The sharper peaks and smoother fluctuations in response maps can lead to a higher PME value. As shown in the line chart, the PME exhibits a high sensitivity to the dramatic appearance change, When challenging issue addressed, the quality of the response map is restored and the index will recover to a reasonable level. After the comparison to the object page and the standardization, the penalty factor for each context page can be calculated, which leads to the correlation filters with high distinguish capability to object against varying background. When new frame comes, the learn filter is firstly correlated with the tracking feature to generate the initial multi-dimension response. By applying the dimensional attention, the initial weight of different channels is computed as ZD. Then, a gating function is defined to emphasize the feasible channels and filter less important ones respectively. Apart from the dimensional attention strategy, spatial temporal attention is applied to capture the spatial nature and temporal cues from responses by following questions along the tracking procedure. Finally, the refined response maps suppress noise, which leads to a robust tracking result. As mentioned before, we express the overall optimization problem in the frequency domain for computation efficiency as a function in the first floor. Due to the mutual independence of different features and dimensions, the overall object function can be decomposed into n subproblems, as in the second row. Finally, by setting the first derivative to 0, the solution to the optimization problem can be calculated with element-wise operations as follows, where the fraction operator denotes element-wise division. Detailed steps of the TSCF tracker can be seen in the left-side algorithm table. We evaluate our proposed TSCF tracker and state-of-the-art methods with the success metric based on the one-pass evaluation. All experiments are implemented in MATLAB R2018A and running on the same computer for fair comparison. The success plot indicates the ratio of the number of frames where the overlap is greater than the given threshold to the total number of the frames. Following the well-known object tracking benchmark, the area under curve is adopted to rank the tracker. Extensive evaluations have conducted on two established UAV object tracking benchmarks, that is, UAV 123 at 10 FPS and UAV DT, with a total of 173 challenging sequences. All parameters remain fixed for all experiments, and we use the source codes of other tracking methods provided by the original authors. First, we conduct the overall performance evaluation on two challenging UAV tracking benchmarks with other 12 methods using handcrafted features. The results show that the TSCF tracker achieves the best success rates in both two benchmarks, which lead to a significant gain compared to other methods. Besides satisfactory tracking results, the speed of TSCF can meet the real-time performance requirements of UAV object tracking applications. The image sequences on UAV DT and UAV 123 at 10 FPS benchmarks are respectively annotated with 9 and 12 different challenging attributes. The results show that the TSCF tracker achieves the best AUC scores in most attributes, especially when the background of the tracked object is cluttered or the object is occluded by nearby moving objects and complex environments. We also analyzed the effect of different values of activation threshold beta T on UAV DT benchmark. The line chart shows the TSCF effectively improves the success rate when beta T is set over 0. The success rate reaches the peak at beta T equals to 0.1, Therefore, 0.1 empirically chosen for the best performance on the challenging UAV sequence. What's more, aviation studies are further conducted to demonstrate the performance regarding to each attention strategy. As shown in the table, the tick in each column denotes that the corresponding module is activated, while the cross means that the module is deactivated. 3 different attention strategies integrated into the origin tracker that show satisfying improvements from the baseline. Finally, the TSF tracker has significantly improved compared to the baseline on both 2 benchmarks. As a result, quantitative experiments have verified the effectiveness and robustness of the proposed framework. Here are several examples of the complex UAV tracking scenarios, including group walking, surfing, running, and crowded junction. Our TSF tracker can keep tracking the specific object when large occlusion or similar object occur. The complete tracking demo can be found on this site. For more details, you can find our code on the GitHub. If you have any question, you can visit our group website. Thank you for your attention.